Alright, so welcome back to another video. So for today's video, we're going to prove that the following two integrals are equal to each other. The improper integral from the integral from 0 to infinity of cosine x squared dx is equal to the integral from 0 to infinity of sine of x squared dx. They're both equal to each other. Now, before we get into the meat of this video, I actually want to prove a tool that we're going to be using, and that's actually, if you recall from several videos, I've actually used this integral, the Gaussian integral. Specifically, the tool we want to use is the following integral is defined. The integral from 0 to infinity of the exponential e to the negative ax squared, where a is some constant, dx, is actually equal to 1/2 multiplied by the square root of pi divided by a, where a is some constant. Now, originally I did the Gaussian integral where our constant is just equal to just 1, so standard. So I'm going to show that this can work for any real number a. So same methods apply. I'm not going to show explain every single detail, but I will give the steps on how to evaluate this specific form of the Gaussian integral itself. So, just like before, what I want to do is I want to just define capital I to be this this improper integral. So this is negative ax squared dx. Okay. So now let's actually square this. So multiply this quantity twice. And then instead, we're actually going to substitute a dummy variable. So this means keep doing it again, it's supposed to be a. Negative ax squared dx. And then multiply, and let's actually use y for this dummy variable. So 0 to infinity of e to the negative a times y squared, then dy. Okay? And then we can actually multiply these two integrals to form a double integral. So that means double integral 0 to infinity of, and then using our laws of exponents, I can just, since they share the same base, we can actually combine the exponents together, which is minus ax squared minus ay squared. But I can actually factor out the constant negative a outside. So that means we'll end up with x squared plus y squared dx dy. Okay, and now what we want to do is to make this double integration easy, we're actually going to be using a change of variables, specifically using polar coordinates. Now, calculating polar coordinates, I'm not actually going to do that. I actually did calculate finding the Jacobian in the other video, so you can actually check that out for yourself on how they how to find the change of variables from there. But just know that when you're changing variables to polar coordinates, using parametric equations, x equals r cosine theta, and y equals r sine theta, and then using our equation for a circle, x squared plus y squared equals r squared, then that means our dx dy, or in this case within the volume, we'll call it d capital A, is equal to r dr d theta. Okay, so now we have that. Let's actually substitute this, but also we have to change our bounds too. So when we're integrating this in terms of theta, so notice that our bounds from 0 to infinity for y, and then x from 0 to infinity. So we're actually looking at the first quadrant of the real value plane, the real plane. So that means changing from these coordinates, we're actually looking at our unit circle, and that's actually being integrated from 0 to pi over 4, because that only focuses on the first quadrant. So I accidentally wrote an infinity, so that's supposed to be pi over 2 specifically. And I think I made a mistake what I said earlier, it's pi over 2. But also our radius, since the radius is infinitesimal, because it's just infinite. So even if you can just plug it in, you get that we're integrating within a big radius. So the radius can be our bounds for r is from 0 to infinity. And with that, so we can just plug in our substitution. dA is equal to dx dy. We just substitute r dr d theta. We can just move that to the front, the r, and then e, then minus a times our square dr d theta. Okay, now all we just have to do is just calculate just evaluate our integral of the inside. Specifically, just focus on integrating this in respect to r. So doing our u substitution, we'll let u equals ar square, then du is equal to 2ar dr, and I can just divide 2a to both sides, so that way we do the substitution, r dr cancels out. So this means over here it's 0 pi over 4 or 2, and then in between it's 1 over 2a, and then e to the negative, and then substitute back our u, which is a r square, and then it's being evaluated from 0 to infinity, and then our d theta right over here. Okay, so now let's actually evaluate our bounds for 1 over 2 half. So 1 over 2a, e to the negative a, evaluated at infinity square. Just and notice that it's negative infinity, so e to the negative infinity is just equal to 0, so this whole term just cancels. Well, actually, this is actually supposed to be minus, so let's see, minus, and then, yeah, this is supposed to be a minus over here. Oops. Yeah, that's a minus over here, and then this should be a minus. Sorry about that. And then divide by 2a, and then what I say, e to the negative a, and then evaluate it at 0 to square. Okay, and notice that e to the 0 is just 1, and then we have distributed negative, so it's a positive, so therefore it's just positive 1 over 2a. And then all we have left is just to evaluate the inside over here. So I think I got room over here. So moving back over here, so we have 0 to pi over 2 of 1 over 2a, and then d theta. But notice 1 over 2a is just a constant, so we're just left with theta divided by 2a, evaluated from pi over 2 to 0. And simply, when you plug 0 for theta, this is just going to be 0, and you plug pi over 2, so it's pi over 2 divided by 2a, which is the same thing as pi over 2 multiplied by 1 divided by 2a, which is just simply pi over 4 divided by a. But that's just only equal to I squared, so I squared is equal to pi over 4a. But when you take the square root, so that means I is equal to 1 over 2, then multiply by the square root of pi over a. Okay, so we just proved our little tool over here, which is going to become very useful for later. So I'll just put a check. So this means now that we have our tool, we're going to show that these two integrals are equal to each other. So now let us recall that Euler's formula, we know that e to the ix is just equal to cosine of x plus I sine of x. Okay, so we're now dealing with the complex numbers. So let's say we substitute let's substitute x for negative x squared. Okay, so this means e to the negative ix squared is equal to cosine of x squared. Now I'm skipping some steps here actually. So if I plug negative x squared into cosine, so we get cosine negative x squared, it's an even function, so it's just going to remain positive. And then if I plug sine of negative x squared, it's an odd function, so that means the negative goes outside, so that means this will be a minus I times sine of x squared. Okay, cool. And this means we can actually establish some parts here. So that means if we take the real of our exponential, so that means the real of e to the negative x squared, or e to the negative ix squared, that's actually equal to cosine x squared. And then if we take the imaginary part, then the imaginary of e to the negative ix squared. This is equal to sine x squared. Okay, now that's nice. Now this means we can just replace our sine x squared and cosine x squares for here. So meaning we take the integral, so the 0 to infinity of cosine x squared dx is simply just equal to the real of the integral from 0 to infinity of e to the negative ix squared dx. And then now we have sine of x squared dx is equal to the well, okay, and then this is actually supposed to be the negative, since we're taking negative here, so it's not positive, so it's the negative imaginary part of e to the negative ix squared is equal to sine x squared. So this has to be a minus over here, and this is the integral from 0 to infinity of e to the negative ix squared dx. Okay, nice. So now that we have that, so now notice that we use our little tool that the integral from 0 to infinity of e to the negative ix squared dx is equal to 1/2 multiplied by the square root of pi divided by a. So now let's actually use that tool for the inside integral here. So notice that there's an I being multiplied by x squared, I being our imaginary unit. So with that we can actually substitute, so this means the integral from, right here, the integral from 0 to infinity of negative ix squared dx is just equal to 1/2 square root of pi divided by I. Okay, but now notice that when we take the square root, well, not yet, we know that I is equal to e to the power of I pi over 2, and that's because you can show this by graphing that complex numbers, 0 plus I, which is basically just 0, 1 if you think about it in terms of the real value plane, your standard Cartesian coordinates, of course. Then when you take its polar form, then it's actually pi over 2 when you're dealing with the angle. Could have said that a little better, but that's fine. But now we take the square root of I, and then we get the principal value is equal to the square root of ei pi over 2. So that's also the same thing as e to the I pi over 4, which that's equal to cosine of pi over 4 plus I times sine over pi over 4. And that's also equal to 1 divided by the square root of 2 plus I divided by the square root of 2. Okay, cool. So we have that. So now let's actually substitute our calculated value of the principal value of the square root of I. So this means this is 1/2. Then that's being multiplied. Well, I can actually move the square root of pi outside, so that's what I'm going to do now. So this means we have the square root of pi divided by 2, and then that's multiplied by 1 divided by our e to our square root of I value, which is here. So 1 over square root of 2 plus I divided by square root of 2. Okay, and let me write the next line here for now, but I'm going to calculate our whatever our parentheses is. So we are basically, we can combine them. We can combine because they share the same denominator. So this means this is 1 divided by 1 plus I square root of 2, which simply flip the reciprocal since it's under division. So square root of 2 divided by 1 plus I. Then I can just multiply its conjugate, just so we don't end up with the imaginary unit under the denominator. And so this is equal to the square root of 2 minus minus I times square root of 2 divided by 2. But also simply that's the same thing, can be rewritten as 1 square root of 2 minus I divided by square root of 2. Okay. Okay, so now that we have our value 1 divided by square root of 2 minus I divided by square root of 2, now we can just substitute this back in. So we have the square root of pi divided by 2, then multiplied by 1 square root of 2 minus I square root of 2. And that's simply just equal to, they share the same radical sign, so I can just combine them into one, so we're dealing with just one radicand. So this is just 1 divided by 2, multiplied by the square root of pi divided by 2, then minus I divided by 2, the square root of pi divided by 2. Okay? Now that we have this, so this is, like I said, this is equal to the integral of 0 infinity of e to the negative I x squared dx. Let me underline this in red, just so. Okay. Now that we have that, now all that's left is we take its real and imaginary parts. So this means the real, I'm just going to substitute our integral with our evaluated. So this is 1/2 square root of pi divided by 2 minus I 2 square root of pi over 2. That's simply just equal to 1/2 square root of pi divided by 2. Okay, and now we take the negative imaginary part of that same integral. So negative im 1/2 square root of pi divided by 2 minus I square pi divided by 2. And simply we take the imaginary part, it's negative 1/2 square root of pi divided by 2 multiplied by that negative, so we get that square root of 2 divided by pi over 2. But also notice that this is equal to cosine of, or specifically, let me write the integral 0 to infinity cosine x squared dx, and then over here is equal to the integral 0 infinity sine x squared dx, which, if you notice closely, the two values equal to each other, concluding that these two integrals are equal to each other, like so. I'll draw the box. You guys can see that, right? Yes, you can. Nice. All right, cool. Now our proof is done, and yeah, good luck. I don't know why I said good luck.